So I think we'll start, and we can start. And if someone is joining, then we can just continue. Or if they're joining late, they can see the recorded sessions.
Yeah, I think we can start, and then people will join slowly, I guess.
Yeah. Can you see my screen?
Yes.
So yeah, I think last time we were discussing orthogonal vectors, and there was a doubt also that in this line, like why there are at most n vectors which are mutually orthogonal, non-zero norm. So, like, did any of you go through it? Like, saw why it is true?
Like, can you just bring back that the line? Let me just open the book.
Yeah. Like, for example, if we have two perpendicular vectors in a 2D plane, how to somehow, prove like whether the third perpendicular line in that plane is possible, which is perpendicular to both these vectors.
Yeah. So one of the things that I tried was like if we can have maximum two linearly independent vectors in 2D similarly. So that we can prove by simply a linear combination of let's say three vectors in 2D. So it will ultimately become like the third vector would be linearly dependent on the first two, provided that they are linearly independent. Now, in terms of orthogonal, uh, I've not tried to prove that, but I'm just getting the same intuition that we'll not find any because we can maximum have two independent vectors. So that is the first meta requirement. Orthogonality is like it's a special requirement. Like two vectors can be orthogonal, may not be orthogonal, and if they're independent, it just fills the space. Um,
Yeah. Yes. I mean, like, yeah, as you said, like, if we have, for example, two vectors in the plane which are orthogonal, then we can perhaps just zoom in and create this create this vector, or rotate and treat these vectors as I cap and j cap, so that any other vector which is, let us say we have some other vector, third vector, we can just represent that vector in terms of I cap and j cap, which is always possible because they form, as we have said, they are linearly independent and uh, cover the entire space. So now we know that this blue vector can be written as linear combination of some c1 into 1 0. I think this is I cap plus c2 into 0 1 plus c1 I cap plus c2 j cap. So, or in general, c1, let us say this is v1 vector in the, so this we zoomed it before to just treat it as I cap j cap. But we zoom out again, I think we have, so this is vector v. And if we do dot product with, let us say, v1, then we get c1 v1 square plus 0, because v1 and v2 were uh, orthogonal already. So this, we know that it is not 0. So we know that any other vector apart from these two vectors in 2D plane, their dot product with these vectors will not be 0. Uh, so
Right.
we know that they won't be, yeah, we won't get another perpendicular vector. And we can generalize this to n dimensions using many techniques like mathematical induction, I guess.
Right.
Yeah, yeah, great. Then last time also we discussed orthogonal matrix A transpose A equals to I. Now let us go to eigen decomposition. So author says here, like the factor numbers, for example, 60. 60 is 4 into 15. So equals to also like 5 into 12. But but to make this factorization unique, we reduce it to the maximum possible uh, representation, like, so that every entity remains the smallest possible entity, which is like 2 square into 3 into 5. Also, we write it in the order of increasing prime factors, and we can prove that this is unique in case of integers. So this kind of factorization is useful for several uh, applications in number theory, in general also, I guess, in cryptography, and everywhere where there is requirement of prime factorization. Similarly, author has author is trying to decompose a matrix. Now here we have seen that while decomposing a number, we are identifying prime factors. And what prime factors are telling is that some unique properties of this number, that this number is not divisible by 7. And these are the only possible prime factors. And that you can identify several properties of 60, the number 60, by just looking at the prime factors. So we have a matrix A, and we want to decompose it into similar smaller factors, which will represent that matrix in some manner and help us to solve problems in applications. So, so here the author has written Ax equals to lambda x, and where A is a matrix and lambda is a constant. So why has author written, I mean, gone in this direction? Can anyone think of it?
At, uh, like at the ax equal to lambda x, like equation 2.39. That's what you're asking.
Yeah, I mean, like, there are several ways to, I mean, there can be several ways to think of while decomposing matrices. But here we are trying to decompose in a particular format. that Ax equals to lambda x. But why were they, going in this direction? Like, how did they find that this is the right approach in the starting? I'm just asking a general intuition.
Yeah. The intuition, right? Yeah. Yeah, I think
Maybe it's factorizing to V and V inverse, right? So AV equals
Okay.
lambda V would be A equals lambda VV inverse, right? So
Okay. Yeah, I mean, like that might be yes. One of the cases that I was thinking is in many applications out there, A represents a transformation matrix, and whenever we have a vector which is like data, we transform that data by multiplying it with matrix A. So in some situations, what so this represents, like, for example, in 3D, this has 3 dimensions, a 3D point. This is a point. This point will get transformed to some other point. So author is interested. I mean, probably they have observed that when does this point, I mean, when does this vector, you can say, just scales up with a scalar factor in this direction. So that this type of transformations uh, are also preserving information of the original data and just scaling by some factor. So these transformations can be special, and for a given transformation, we can find such points x such that this is possible. Probably this is the intuition. I don't know.
Yeah. So yeah, right. So I was also thinking similar like as you rightly said. So any matrix to vector multiplication can be thought of transformation. Like in this case, we have a point 3, 2, and then we are trying to project this in a different space. Basically, just transforming it to a different coordinate. Now, basically, this matrix to vector multiplication essentially does two things. It rotates the vector and it scales the vector. Every time it does that at the end of the day. Now, there are some special vectors which just get stretched. It doesn't get rotated. And that is what we are interested in. And there are different applications for that. Let's say image resolution change, stretching of an image and all that things. So basically, just rotate and scale is the main thing which happens due to transformation. Now, we are interested in eigenvalue and eigenvectors and why they are special. Because they have a special property where it just scales, doesn't rotate, and that actually captures a lot of information in a real world in terms of variance and all that.
Yeah. Yes. Yes. So I think they have taken this concept and all the vectors for a given matrix A, all the vectors satisfying this equation uh, are called as eigenvectors, and corresponding lambdas are eigenvalues. So if we just multiply, instead of x, if we take some constant into x, cx, and that c will get cancelled out. So this is always satisfying the equation. Uh, then then here it is directly written. We can write A equals to V into this matrix, which contains all the lambdas. Into V inverse. We can think this of, so this is nothing but just concatenation of everything. Like AV equals to, I think, AV equals to V lambda, I guess that, where and A is same, and V is like matrices consisting of eigenvectors. So you can just see that this vector, this is some, so you can see that the first equation A is completely involved. So basically, when we multiply a matrix with a single vector, so n cross n and n cross 1, we get again n cross 1 matrix. So we can think this first column as the multiplication of A with this first column, which will be multiplication of this with this first column, I mean, which will give us lambda uh, lambda v1. It will be a v1 equals to lambda, because lambda is scalar. It can go to the left. So the same equation, this is just representation of this equation. Then
Yeah, so Amit, I think Sujit
yeah,
has asked one small question before we proceed. I think that's a good question.
okay.
He's asking that will it be accurate to say eigenvalue decomposition represents a linear transformation? No, okay, yeah. So first of all, linear transformation is nothing but a vector when gets multiplied with a matrix, like matrix and vector multiplication. That's all. Right? So anything matrix into vector multiplication is a linear transformation. So that's the only definition. Now, eigenvalue and eigenvector. This is when we say a matrix getting multiplied with a vector, we get another transform vector. Now we give one vector as an input, we get another vector. Now there are some special cases. Most of the time, not most of the time, all the time, when we give one vector, the output vector, it's a rotated and stretched. Now there are some special vectors where rotation doesn't happen, it just stretches. So those are the vectors we specially term as eigen vectors. And by how much they get stretched or shrinked, that is called eigen value. That's all. That's the definition. Now, eigenvalue decomposition is just a decomposition technique, like how I can make a big matrix and decompose it. And one of the reason that Amit also was mentioning the early, I mean, at the start, there are lot of things that we need to do with the matrix, which is very hard to work on, like in a random matrix. Now, eigenvalue decomposition helps to solve that problem. Like, let's say we have to deal with a matrix of 100 by 100 and we have to find a power 1000. So how can we do that? So things like this. Now, eigenvalue decomposition is completely separate from eigenvalue and eigenvector. That is we are just using that special vector and eigenvalue to use for our decomposition. And since we are using eigenvalue and eigenvector, we are calling it as an eigenvalue, eigen decomposition. Similarly, we have SVD as well. SVD is more general because it is applicable for any kind of matrix. Eigenvalue decomposition is specific to square matrix. It's like, in other words, eigenvalue decomposition is also termed as diagonalization. If any matrix is called, if somebody says a matrix can be diagonalizable, we say that okay, it can be decomposed using eigenvalue decomposition. So eigenvalue decomposition, in short, the name eigen came just because we are using eigenvalue and eigenvector of a matrix. That's all. And everything is transformation. Whenever we multiply a vector with a matrix, we get another vector. That's a transformed vector.
So it's guaranteed to exist for any square matrix.
This for eigenvalue decomposition, if we have a square matrix with non-zero
Determinant.
lambdas,
Yeah,
then
okay.
only it exists. If non-zero lambdas, in the sense, that means the square matrix is all the columns are linearly independent, and
Okay, okay,
yeah.
yeah.
So
Okay,
so and one last thing, this is the constraint that we have with eigenvalue decomposition, that it has to be a square, it has to be linearly independent. These are the issues, and that's why we have SVD, which is generic for everything, right? So that's a kind of a more generic thing.
okay. Thank you. That's good.
One more thing I wanted to add up to this is that let us say we considered scaling and rotation just for one point. If there are multiple points, which generally a matrix represents like multiple points, which is not a vector. So if we like even scale, let us say this with every if you scale every point by a different factor, let me just do this black. So let us say this goes here. Let us go. This goes here. This goes here. This goes here. So even if we are scaling every vector, the entire matrix, we cannot say whether it is entire data set, entire points are rotated on. So in this case, like you can see that blue ones represent a matrix, and when you multiply a matrix by another matrix, which is a transformation, uh, it might uh, every point is moving differently. So the entire group, we cannot say that it is rotated or not.
Right. It may be. Okay, okay, got it. Right.
I
Yeah.
have a question. So, Suman, did you say that it eigen if you're doing eigen decomposition, then it is only limited to like what Sujit has asked, right? Scaling and not rotation, because I assumed that when you do a linear transformation, you can
Rotate as well. Yeah.
it as well. Sharing is also possible, right?
Right.
Yeah,
No.
of course.
Yeah, yeah. That was my mistake. Yeah. Okay.
Oh,
So
Yeah.
that is possible. So that's transformation will always be like that, everything, right? But I'm
right.
talking about the eigenvalue and eigenvector, which are used for that eigenvalue decomposition. So when you have a matrix A, uh,
Yeah,
we break it down with, let's say, P lambda, P inverse, whatever it is, that we are decomposing that matrix A with three different metrics, right? Or two
hmm,
metrics.
yeah,
So when we create those metrics, three different metrics or two different metrics, we are using the eigenvalue and eigenvectors of A, right?
right.
So I'm just talking about that eigenvalue and eigenvectors. Yeah, that those just scales, but A,
Yeah.
that whole matrix, that is just do any transformation, just like how Amit is showing here, right? So that has nothing to do with only scaling or only rotation and all that.
Okay. I was just like trying to get a clarification.
Yeah, sure. Yeah.
Thank you.
Okay, so uh, so this is defined only for square matrix. Here, mainly because I think yeah, why is this defined for square matrix?
That's a good question, but I think this is for this one, right? We need to have eigenvalue and eigenvectors, and we cannot have a eigenvalue, eigenvector for a non-square matrix. And I read it like,
Yeah,
right? And I read it in a book that the intuition that got started with this is AX equal to B, AV equal to lambda V, the equation number 2.39. So this was a very simple thing, right? When we multiply a vector with a matrix, we don't have to do any computation. We just take that vector and multiply with a number, just a scalar number, right? So then they thought that, okay, why can't we take all the vectors and just put everything one after another?
Yeah.
So in place of AV, let's replace V with all sets of V, different V's, right? And create that matrix. And that's how this equation end up happening, like 2.40. And eventually it became such that we found a diagonal matrix in the middle, and then since it is symmetric, it actually goes beyond, like V inverse is V transpose, so it becomes very easy. Like you give one matrix, complex matrix, the only condition is it should be square, and the column should be linearly independent. That's all. And then with this condition, we can solve a lot of complex problems. Now, for other cases, we have SVD.
Yeah, so basically, in this case, it is not diagonalizable, or you can't decompose it in this in this neat form, right? That we have. So that's why it doesn't work for non-square matrices. But as Suman said, yeah, SVD for all other matrices, SVD is commonly. This is when a square
yeah,
matrix has like eigenvalues and eigenvectors, and we can easily put them in this form, and this calculation becomes quite simple to work out.
yeah. I think even while solving for eigenvectors, one of the techniques is just to bring back and multiply with identity matrix, right? So I think identity matrix is also a square matrix, and I think determinant is also defined on a square matrix. If
Yeah,
we if we assume that x is not 0 because x equals to 0 always satisfies, uh, then this has to be 0. So uh, yeah, I
yeah. So
mean, I think
to find the
determinant should,
polynomial, right, through this, and then find.
yeah. So yeah, and this represents like a matrix multiplied by a vector x vector is giving 0. So if the matrix is in some particular dimension, let us say it represents data in 3 dimensions, then probably we are getting the output in lesser dimensions, which is the result of 0. That is the reason, I guess, we do determinant equals to 0 and solve for lambdas.
Actually, can you repeat that, the
Yes.
last part, where
So
why we take the determinant? That, like, you mentioned something before that.
yeah, so we have one vector x, and we are transforming it such that it becomes 0.
Okay.
So this transformation is kind of reducing the dimensions of such vectors x.
No, so I mean, what do you mean by dimension here? The vector dimension you're saying?
Why will it?
Actually, the vector x can be if the matrix, if this is in n dimensions, the x vector represents a point in n dimensions.
Right.
And if the matrix is transforming into 0 always, then in that dimension probably it is acting as a 0. I mean,
So okay. Yeah, I got that what you're saying. So let's a step back. Okay, so let's look at your first equation. Okay, the first one, ax equal to lambda x. Okay, so let's think about this equation. Why we came up with this? We knew that ax will give b, right? B as a different vector, something else. That was always the case, which Sujit mentioned. Like it just do the transformation. Ax equal to b, right? That's the mother equation, small b. Yeah. Now we realized when we take x from in R2, Rn, whatever, right? And we assume that A is a square metric. That is the first assumption. Okay, so we are not talking about rectangular or any matrix. Now from here, we found out that there are few vectors which stretches only stretches. So that's where we replace B with lambda x, right? Now we are interested to know what is that lambda, right? So what is that lambda and what are those special x? And that's when we took lambda x in the left hand side and we got this equation ax minus lambda x equal to 0. Now from here, uh, we use this bracket, which is your second equation, right? And I write it in this way. And the reason is uh, x cannot be 0 because x is if I take x 0, 0 is a 0 vector. So what can we transform to a 0 vector? So that's why a 0 vector is never an valid eigenvector, but eigenvalue can be 0, right? And so that's why this a minus lambda x, that we have to make it 0. And that's how this characteristic equation came, a minus lambda I equal to 0. This equation came because x cannot be 0. We cannot assume x 0 because that is not giving us any information, right? What we can do with x equal to 0. And that's how we found that eigenvalue vector.
so just want to add up here. I mean, yeah, x cannot be 0. So this matrix multiplication has to be 0, right? I mean,
yes.
This is a matrix. This is a vector. So this is not 0. Its product with x is 0, right?
No, since x cannot be 0,
This has to be 0.
Have in the brackets should be 0. All for it, right?
No. For example, if we have, let us say, 1 0 minus 1, and if we have 3, 3, this will be 0.
Not linearly independent.
Yeah, not linearly independent. Okay, that is the case. But even if like x is non-zero, we cannot say that this is 0.
No. So here, see this a minus lambda I, right? That the equation that you have written, a minus lambda I. To make this equation a minus lambda I x equal to 0, right? We have to make either the first part 0 or the second x is 0, right? We have to make one of them has to be 0.
To make the whole thing 0.
To make the whole thing 0. Otherwise, you cannot do it. And there is absolutely no relationship between A matrix and A minus lambda I matrix. There is a completely different matrix. There is no correlation, no connection. they both are same matrix only when lambda equal to 0.
That's 0, yes.
There is no theory for anything that exists between and the another matrix A minus lambda I. Now, in this characteristic equation, I have to make this equation as 0. How can I make 0? So there has to be some way, and the determinant we find it at 0 is what. So we can try. We can take some counter example and see if we can make it 0 somehow, and then we can with a non-zero x.
Yeah, you can also
Yeah.
come at it from simultaneous equations, right? So, if you have a system of
Yeah.
equations, it has to be equal to the number of unknowns, right?
Yeah.
And they should be linearly
Yeah.
independent to solve it.
Yeah. I mean that is the like that is the reason I took this vector, but it is simple 1 minus 1, that is why it's looking like this. But I guess there are so many vectors possible as as we said, like three. If there are three simultaneous equations and if we get the solutions of them, we can write the
Yeah,
those equations.
but this matrix 3 0 3 4 0 1 5 0 5, right?
I think the determinant is 0 for this. Looks
For
like.
this also determinant is 0, right?
Yeah.
Yeah, determinant is 0, but the matrix is not 0.
Yeah,
Is what I'm
matrix.
saying.
So okay. So we got it wrong. So we have to make it 0. So how we can make it 0 is we used determinant to make it 0. It's not the 0 matrix. Right? So that's yeah, then it would be similar to making x as 0, right? Yeah.
Yeah. So like what I was trying to say is, since the product of a matrix and a vector is 0, so that probably means that this matrix is trying to reduce uh, the space that is covered by X. I don't know.
Okay, I got it. What you're trying to say. So what you're saying is this, okay? And now I completely got it. What you're saying. You're saying this, that if I have, let's say in this example, we are transforming a vector from R3 to R3, right? But we are just reducing one dimension out of those three dimensions, right? And the reason is the metrics that we are multiplying, they are not linearly independent. The columns are not linearly independent. So although the vector dimension are same, R3, this is also R3, this is also R3, we will always get the same dimension vector, but we will lose one of the dimensions. So, for example, if I take a 3D, right, well, let's say a football, right, all the vectors in the surface of the football, and then when we transform it, we will get all vectors, but in a sheet of paper, right?
Yeah, so you use values in the vector, but it will still be a
Yeah,
3D. Okay, so you're
kind
saying
of
0 vector, but it's a 3D
volume.
of 0.
Correct. Yeah, kind of volume, right?
Okay, volume, correct.
Yeah. So like sheet of paper has 0 volume, but football was having volume.
Hmm.
Yeah.
Okay.
Yeah. So no. Okay. See what I see. This is when I say football. That football doesn't belong to the matrix. The football belongs to that vector. So all the vectors in R3, right? I can take any vector like 1, 0, minus 1. So this vector could be any vector, like all vectors in R3 that exist, right? I will multiply with this matrix and I will get all the vectors in a plane.
Yeah.
Right? So matrix is a transformation. So that will remain the fixed. I will pass on all the vectors in my space, and my space here is R3. So that will be all vectors in that space.
Got it. I think even the determinant, there was one line that determinant represents uh, measure of how much multiplication by matrix expands or contracts the space. So I think they
Right.
have used that to, because it is reducing the space probably, that here the space is 0 on the right hand side, so left hand side also space should be 0. So if we take a matrix with whose determinant is 0, then it will represent a lower dimensional space probably. So the volume in that dimension will be 0. I think
Yeah.
we can continue ahead. It's like, and if you have anything to discuss, let me know.
Yeah, can you just take a fresh page? I will just tell you, it's a yeah. Can
Okay.
you just on the left hand side, can you just draw XY plane, just a XY plane? Yeah, and maybe you can put one Z axis as well, just like that. Yeah,
Okay.
yeah, right. That's all. And then on the right hand side, you just draw the same XYZ plane. Yeah, and in the middle, you can draw that matrix A, with 3 columns and one of the column, I mean, just with 2 independent columns. Right? The last matrix, that the example that you have taken, right? Uh, any random example, you can, any matrix, just linear columns should be dependent. That's all. You can,
Yeah, I'll take the previous one.
yeah, previous one, right now. Yeah, so here, if you now on the left hand side, this is my input space, and the right hand side is the output space, and this is my matrix, right? So in this space, in the left hand side space, which is the input space, and it is in R3, that means any vector I can take. So here in the center, we can draw a sphere, right? Like on the paper, it will look like circle, but it's a sphere, right? Now, when we multiply all the vectors on the surface of this sphere with this matrix, what I will get on the right hand side, transformed vector, it will not be a 3D space. It will just relinquish one of the dimension, right? So
Okay.
That's because of the middle 0, though, right?
correct, exactly right.
So it will be like this, kind of flat.
Right.
Yes, sir. Okay. Uh, Okay. Okay. So I think, yeah, that is the reason we are doing determinant 0 while calculating eigenvalues. Okay. Great example. Great. So yeah.
In fact, we can actually see which dimension we are squishing. We are actually squishing the y dimension because the second column is 0, right? So if you put any in this orange matrix, if you write any vector on the right hand side, you will see that the second column gets zeroed, right? So yeah, wide, exactly, that the arrow that you mentioned, we're just squishing it.
Yeah. Yes. So
Yeah,
it's like,
and go ahead.
yes. Cool. So so this is the eigen decomposition of square matrices, which we can do. Right. Uh, okay. Now they have said that if you have a real symmetric matrix, it can be decomposed into real valued eigenvectors and eigenvalues. Any idea why this is the case? So if you have a real symmetric matrix, it can be decomposed into real eigenvalues, and the eigenvectors also are real. So I think one of the, can anyone think of this? I think those I can go ahead. Hello.
What you're looking for, Amit? I just missed that.
So they are saying that real symmetric matrix. So matrix which is symmetric in nature, that is transpose is equal to itself, and that all the entities are real. Its eigenvalues and eigenvectors are also real, consist of real numbers. So I think one way to prove that is to analyze the conjugate matrix of a vector, I mean vectors multiplication with this. So this is if X is a vector, if with complex numbers, let us say then X conjugate is just taking the conjugates, and then X conjugate transpose X will be nothing but, so let me just click. Will be nothing but the addition of norms of individual elements. So 1 plus I, 1 minus I plus 0 into 0, I into minus I, which is 2 plus 0 plus 1, which is 3. So this is kind of norm of, this is kind of the magnitude of the vector in when we are dealing complex numbers. So yes.
Nothing.
So we can just multiply with lambda. We are dealing with the real symmetric matrices, and we'll try to prove that this is equal to lambda bar conjugate, so that we'll get lambda equals to lambda bar, which implies lambda is real. So we'll try to prove this.
Yeah, nice.
So this is equal to, if we rearrange this is equals to, because since lambda is a scalar, we can just place it anywhere. And I mean, it is associative, as you have seen earlier. Lambda x you can replace with ax, and
Okay.
a you can replace with a transpose. Lambda x equals to x is already given, like we have assumed already. Then we know that it is real. Since it is real, we can replace a with a conjugate only. So this is nothing but ax conjugate transpose x. Wait,
Sorry, how is A equals to A conjugate?
because it's we are assuming it's real.
Real just means
Real.
includes all of the numbers, right?
Huh? Yeah,
Ah,
yeah.
real just means it includes all of the numbers, right? But how is it A equals to A conjugate?
So a conjugate is just taking conjugate of all elements.
Hmm.
So if it is 1 minus iota, all elements are there, then A conjugate will consist of 1 plus iota, because a conjugate of imaginary numbers, they get get multiplied by 1. So since we already know that A is real, it means that there are no elements like this. All the
Oh,
elements are real in A matrix, real numbers, which is of practical use also. Like in practical applications also, we have real values.
okay. Sorry. Yeah, that clarified my question.
Yeah. So since A has all real values, A conjugate also has all real values, and A equals to A conjugate. Then we can write this as in AX conjugate transpose X, and we can again replace AX by lambda X. Then if we again remove the bracket here, we'll get, since lambda is constant, lambda bar will get uh, outside. So what we have proved is this thing. Now we know that, now we know that pardon my handwriting actually. We know that this quantity is not zero. We have assumed x not equals to 0, and we know that this is non-zero, as we have seen earlier in this case. It is basically the addition of magnitude of all elements, squared magnitude. So
Yeah, it's like
this has magnitude of root 2. So here we got 2 in the solution. So like this is always positive. This is not 0 basically. So this has to be 0. So we got lambda equals to lambda. So eigenvalues of these matrices are always real. And similarly, I think we can prove that eigenvectors are also real. Now, can you think, so there is also mentioned here that these matrices are orthogonal. Can you think of a way of proving it to be orthogonal? Hi, am I audible?
Yeah, you are.
yeah.
Can we take
Yeah.
a dot product of that, or
Yeah, dot product, yes.
Vectors have to be the dot product of the vector have to be 0, right?
Yeah, dot product of all the columns or all the rows should be 0. any direction where how to proceed to prove orthogonality of this type of matrices?
So we,
So what
yeah, go ahead.
we can just take two vectors, two columns of this matrix x1 and x2, and we can again analyze this quantity, which is like the dot product of the two vectors. Now, if we multiply with this lambda 1, right, which is eigenvalue corresponding to x1, then I mean lambda 1 is also lambda 1 transpose, because there's nothing as transpose actually. So we can write this as lambda 1 x1 transpose x2, and lambda 1 x1 is again ax1, because it satisfies since it's an eigenvector. Uh, yeah, I mean, sorry, we have to take two eigenvectors x1 and x2, not any columns.
Yeah, basically the eigenvectors from the orthogonal matrix we are taking and we're trying to prove it, right?
Yeah, orthogonal of this eigenvectors of this matrix will always be orthogonal.
Hmm.
So if we take two random eigenvectors and calculate this quantity, uh, this will be here. You can just take the transpose A transpose x2. Now A transpose is equals to A because it is symmetric. Because it is symmetric, and you can write ax2 as lambda to x2. So lambda 2 will come outside. So this will mean that lambda 1 minus lambda 2 x1 transpose x2 equals to 0. So since lambda 1 is not equals to lambda 2, because these both are different eigenvectors, we can say that x1 x2 equals to 0, which means that x1 is perpendicular to x2.
Yeah,
So
interesting.
yeah, so I mean, do you want to take a look, or should I proceed?
Yeah, I can proceed. This is good. Yeah.
Okay, cool. So we have seen that every real symmetric matrix can be decomposed into real valued eigenvalues, and this Q matrix is orthogonal here. Mm. Actually, this matrix Q contains eigenvectors of A. So the columns of matrix Q are basically eigenvectors of A. Okay. Yeah, as we were seeing in the factorize of 60, we were writing in the smallest to greatest format. Similarly, by convention, we usually sort the lambdas in descending order. So lambda max first, then lambda min in the last. And you can see that lambda max represents scaling in a particular direction with the maximum magnitude. So since it is scaling the data by so much magnitude, it is kind of the main and major aspect of the transformation. So, so if we want to just analyze what transformation A is doing to some vectors, we also get that idea from the lambda max. This diagram, I think it's fine, right? There are two lambda 1, lambda 2. Lambda 1 is greater than lambda 2. So there is more scaling in this direction. Okay. Matrix is singular if and only if any of the eigenvalues are 0. So yeah. Then quadratic expressions of the form f of x equals to x transpose ax subject to norm of x is 1. So eigen decomposition is used to optimize such f of x. Okay. Yeah, here you can see that if we replace x by eigenvector of a, then ax becomes lambda x and x transpose x is 1 because norm of x is 1. So f of x becomes lambda. Okay. Then if the matrix is positive definite, then positive definite means all the eigenvalues are positive. Positive semi-definite is not all the eigenvalues are non-negative. So even 0 is included. Similarly, negative definite, negative semi-definite. So if the matrix is positive semi-definite, then they guarantee that x transpose ax is greater than equal to 0. Anyone has to comment on this? Like, how is this?
Is it because ax is lambda x and lambda is always positive, and x transpose x, it would be just a square, so it would be always greater than 0.
But okay, but it is given for all x, right? Not just eigenvectors. I
Yeah,
guess.
yeah, for any x, ax, mm,
Yeah.
yeah,
Idea.
mm,
Because it will be equal to lambda x for eigenvectors.
mhm. Right. Mm. But the metrics, the matrix was formed using the eigenvectors, right? No, or no? Or it could be
Mm.
no, I'm wrong. Sorry. Yeah.
I think we are talking about general matrices in this
Correct.
paragraph.
Yeah, it's general matrix, right? Yeah. So when we say the eigen a matrix whose eigen values are all positive or positive definite. Okay.
Mm. I think we can use linear combination, perhaps.
Wouldn't the definition imply that x is an eigenvector? Or Ax is actually reducible to lambda x, because it says a matrix whose eigenvalues are all positive is called positive definite, and then it says positive definite matrices. So it would kind of imply that these matrices have eigenvalues, and therefore they have they satisfy the equality Ax equals lambda x.
No. So for all x, they have mentioned it here. I mean, I think we can use that property that you're suggesting, right? That Ax equals to lambda x for eigenvectors when x is eigenvector. But when x is not eigenvector, it can be represented as linear combination of eigenvectors.
Okay.
And I think we can use that, I guess.
Yes.
So we know that x transpose Ax, every x can be represented as some linear combination of eigenvectors. I think can we do this directly, or so? For example, if there are like two eigenvectors, you can say C1 V1 plus C2 V2 transpose A. So A. So this C1, okay. So every element of A will get multiplied by C1 and C2 both. So because these are constants which are applied to all the elements of these vectors also, we can take the constants out. I guess we can write this as C1 square, C1, C2, C2, C1, and C2 square. So these are the four coefficients of all the elements of matrix A. From left, C1 will come, from right, something like that. And now we can represent. Okay. Yeah, sorry. Actually, we can do this directly only now. So this is C1 V1 transpose plus C2 V2 transpose A, and the right hand side, this we can simplify. This will become C1 A V1, we can write lambda V1.
Okay.
And that will be lambda 1 V1 and lambda 2 V2. Now, yeah, now we can just multiply. Now we know that V1 or V2, V1 and V2 are orthogonal. Uh, because every eigenvector of, as we have seen this here, every eigenvector of real symmetric matrix, I mean, they are orthogonal in nature, different eigenvectors. So V1, V2 are orthogonal. So this and this multiplication gets 0. And similarly, this and this is 0. So we have C1 V1 transpose V1 C1 square lambda 1 plus lambda 2 C2 square V2 transpose V2. Now this is positive. Lambda 1 is positive because it is positive definite, positive semi-definite, sorry, greater than or equal to 0. This is also greater than or equal to 0. So we can say, I think, greater than or equal to 0. I think we can generalize this concept for n vectors.
Cool.
Should I proceed?
Yes.
Okay. Similarly, I think we can show that positive definite, okay, so this is greater than or equal to 0. And if it is exactly 0, then we can show that x is 0. I mean, here also we can see that if this is exactly 0, then since lambda 1 is not 0 and C1 is not 0, this should be 0 and this also should be 0.
Yeah.
Okay. Okay. Let's come to the next topic, singular value decomposition. Now, the problem with previous approaches was that it was possible only for square matrices, eigen decomposition. But now we want to deal with every real matrix, which is not necessarily square. So instead of analyzing the eigenvalues, we want to decompose into this format where A is m cross n matrix. So A is m cross n, U is m cross m comma n, then D is m comma n, and in the last D is n comma. Okay. Hmm. The matrix D is a diagonal matrix, but it's not necessarily square. So if it is a tall matrix, then these are the non-zero elements. The rest all elements are 0. Okay. And the elements of D, non-zero elements, are known as singular values. So they are like kind of eigenvalues. They are not eigenvalues exactly, but similar to eigenvalues. So these are the singular values, and U contains vectors, columns of U. These are left singular vectors, and V also has columns which will represent right singular vectors. Now, left singular vectors are eigenvectors of AA transpose. Now you can always see that AA transpose and A transpose A are always square matrices, right? And so since there are square matrices, we can find eigenvalues, eigenvectors. So this will give us U, and this will give us V. So yeah, anyone want to discuss here?
So this one, so when you do SVD equals, like some A equals UV or U DVT, right?
Yeah.
What it's now saying is that U is actually like the eigenvector of A transpose, yes? And VT is the eigenvector, or A transpose A is the eigenvector of V on the right singular, yes?
Yeah. Yes.
Okay.
So yeah, so we are representing A as U D V transpose, and U will contain columns which will represent eigenvectors of AA transpose.
Yes.
So this, and similarly, this will represent eigenvectors of A transpose. Yes. So and what is D is the square roots of eigenvalues of A transpose.
I see.
So this can be rectangular. So this is kind of root lambda 1, root lambda. But lambda is uh,
The eigenvalues of A
yeah,
transpose.
these are the lambdas basically from
Okay.
these equations. Yeah.
So when you square it, those are the scaling factors, basically. The lambdas are the scaling factors. When you,
Yeah, I mean, it is interesting to see that, as you're saying, that this has a scaling factors of lambda in some direction I, and I don't know how in the ith direction or direction corresponding to ith eigenvector. Okay, because
Yeah.
this is uh, yeah.
Yeah,
Tell.
it's yeah. So it's actually that what you just said. So here, when we say AX, right, on the left hand side, AX, when we had just one matrix, we used to scale and rotate both. This matrix used to do, But now we are
Yes.
just dividing it into three different metrics. But now what we know is we exactly know which matrix does what. The first matrix will rotate a little bit in one direction. Then in the same direction, whatever is the rotated vector we get, the middle matrix will stretch it, and the last matrix will again rotate it. So, but now we are more definite on every aspects of that transformation, which A was doing magically.
Okay, so you're saying this will rotate, this will stretch,
Yes, this will again
this
rotate.
will again rotate.
Correct.
Okay, interesting.
So you can see this if you open this image. I'll just sharing the link. Maybe you can just open it. I mean, this is available in images, any images like Google image.
Okay, okay. Okay, let's open. Okay, this
Yeah, this is the one, right?
is this the one that you're
Yeah.
looking for?
Yeah, this is the one. Yeah.
Okay. So the middle one is stretching. Yeah.
Because in middle one can only stretch because it's a diagonal matrix with diagonal elements, right? So it can only stretch.
Oh, yeah, yeah, yeah. Yes, yes, yes.
And if you see this, now that this also tells uh, more things about our transformation, because if we have zero rows or zero columns, I mean, it's let's say this middle matrix is not a square matrix, it's a rectangular matrix, then it will surely add some dimension or reduce some dimension, right? So that also we can figure out from there, because the first
Okay,
matrix and last matrix are always square, so we are sorted there. So they'll be on
okay,
the same space, right? It's if it is Rn, that would be also in Rn. The middle one is only adding or removing the dimension from the vector.
okay, okay. Hmm. Can we say that since we had orthogonal matrix, I think no, in this case we had because in orthogonal matrix or even in symmetric matrix, A equals to no in yeah orthogonal and symmetric.
No, you're correct.
So
It's A transpose equal to A inverse.
then we have determinant of A square equals to 1, which is determinant of A equals to kind of 1 minus 1. So which means I mean like will the lambdas be like 1 or minus 1 because it's not scaling only rotating of u and v.
Correct.
Will the
Yes, because U and V are the, are formed by symmetric metrics. These are symmetric metrics. One is A transpose, another one is A transpose A.
yes, yes.
Both of them are symmetric metrics. So all the properties of symmetric metrics will apply to this A and V.
Oh, okay, okay. Yeah, yeah, nice observation. Yeah, I did not realize this. Yeah, I mean, yeah, because they are orthogonal and symmetric. I mean,
Right.
so
So that's why we
mm,
change it to a unit norm, basically.
but U transpose equals to
Mhm.
V, right? U transpose equals to V, right? Because A transpose,
Mm.
we take transpose, it will become A transpose A, which is V. So U transpose not necessarily is U. I was saying for the symmetric. I mean, if U is just rotating, not scaling, then should it have lambdas as one, or all lambdas?
No, so here we are talking about the U matrix, right? So the U is A transpose, right?
Yeah. Yeah.
Yeah. So the now we are talking about the eigenvector of A transpose, right? What it is,
Yes.
right?
Yes.
Yeah. And the eigenvector of A transpose is same as the square root of the matrix A, right? The eigenvalue of matrix A.
Yeah. Sorry.
Yeah.
Eigenvector.
Yeah. So what I'm saying is this U, the eigenvalue of this U is nothing but the eigenvalue of A transpose.
Yeah. 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 Yes. Yes.
Now you are asking that whether
Yeah.
these value would be always 1 or -1. No, there is no such thing. It can be anything.
Yeah. I was asking because since it is not scaling, only
Oh, okay.
rotating.
Okay. Got it. Okay, why are you saying that, right? Yeah, okay.
Yeah. Yeah, yeah. I mean, but still not sure. Like if that is the case, like lambda, because even they have not mentioned, and I don't see it direct also. Like,
Yeah,
is it?
I got it. Let me just think, draw something.
Yeah.
Yeah. Right.
Mm,
Good point. Yeah.
okay. So I think I can. Are you doing this, or we can just look
Yeah. So
for
we can
what
do
is
it. We can
this?
continue. I'll post
Yeah.
something
Yeah.
if I come out with something on the Slack. Yeah.
Yeah. We can perhaps even discuss in the next session. Like if what are the lambdas of U and V?
Yeah. Sure.
Are they? Yeah. Okay. So coming next to pseudo inverse. So this is defined for matrices which are not square as well. And the definition, as you can see here. Okay, first they have said if A is taller, if A is taller than it is wide, then probably there is no solution because number of equations are greater than number of variables. So even if one equation is, there is high chance that uh, there won't be any solution, right?
There can be
And if
multiple solutions, no?
no, it's like 2x plus 1, sorry, 2x plus y equals to 3, then 4x plus y equals to 4. Now, if I write 5x plus y equals to something which is not coming out to be true, let us say 8,
Oh, I
then
see. Okay. You'll never get.
then there are only two variables but three equations, so it is highly probable that there is no solution itself. Uh, And in the other case, if there are more variables but less equations, then there can be multiple possible infinite solutions.
Okay.
Yeah. Now, the definition of pseudo inverse, as you can see, if you put the lambda here 0, then it is coming out to be A inverse. That is our target. Like if A is a square matrix, this is even valid. But which is what we want in inverse. So we have defined pseudo inverse as V d plus U transpose, where D is equal to singular value decomposition of A, UDV. So A is UDV transpose.
Can I ask what's the strange arrow under the limit? Is it just I don't know, not straight, not a straight arrow? I've never seen this notation.
Yeah, even I have not, even I don't know what it is. Generally, it is horizontal.
Yeah.
I have no idea. I have to.
Maybe it's there in the
Uh,
notation page in the beginning, I don't know. But I'm also assuming it's the tends to notation itself.
yeah, it is probably that only. I think I don't know why they have given this, but it's probably that only. Alpha tends to 0. Let me just check the notations if something is there and not. No, nothing is there. I just saw the notations. Probably it's a mistake, but I'm not sure why, because this book is very old and uh, technically I don't expect mistake in this book at least. Not that sure. Okay. Um. So here U, D, V are from the singular value decomposition of A, and D plus is obtained by taking reciprocal of its non-zero elements, of these non-zero elements, and then taking the transpose. So if the matrix D is, if the matrix D is 3, 4, 5, 0, 0, 0, then what will be T plus? T plus will be,
Transpose of the reciprocals.
yeah, 1 by 3, 1 by 4, 1 by 5, I guess. Am I right?
Yeah.
Oh, yep.
Okay. So when A has more columns than rows, that is wide matrix or fat matrix. This pseudo inverse has many solutions, and x equals to A plus y is the minimum, is a solution with minimum Euclidean norm. Has anyone any intuition about this? Like, so what they are saying is uh, if we have a matrix A which has more columns than rows, then x equals to A plus y, where A plus is defined as we saw VD plus U transpose. They are saying that x equals to A plus y is solution with minimum Euclidean norm. This is a solution of Ax equals to y.
But they just said that it can have multiple solutions, this set of. So is it the one that is closest to the origin that they're taking? Is it like, by convention or something?
Yeah, they are saying that this is the solution. Although this equation can have multiple solutions because this is wide matrix, they are saying that this particular solution is providing the minimum norm x. But any intuition about that, like why is it providing minimum norm? When I have not gone through this bit. If anyone has any intuition about this, please let me.
Oh, it says in the last line, right? In this case, using the pseudo-inverse, gives us the x for which Ax is as close as possible to y. So,
Yeah.
It's the transformation that gives you the closest to the result.
No. Yeah. So the below one is of a tall matrix.
Oh, I see. Okay.
If it is a tall matrix, then the pseudo inverse, if we use this, we get an x for which Ax is as close to y. So that is minimum of Ax minus y. Okay. If anyone does solve it, does get an intuition why is this the case, we can discuss it in future also. So just let us proceed further. Trace operator traces sum of diagonal elements of the matrix. Now, trace operator provides alternative way of writing Frobenius norm. So Frobenius norm we saw was summation every element aij square and then taking under root, right? So I think in AA transpose, these all elements will come. Yeah, mostly because when we say A transpose, then I mean, if you want ith element of A transpose, ith diagonal element, that will be just multiplication of A Aij square equals to 1. So all the squares are multiplied and added. Yeah, I think this is easy to prove. We can prove it later. Again, transpose it's invariant to transpose operator. Trace is invariant. Then, yeah, trace of a square matrix. So if it is a square matrix, even the cyclic multiplication doesn't affect the trace. So, so if we prove this, even this is done. So because we can write A, B, C. I think this is also not that hard. It's easy to do. Anyone wants to discuss anything till here? Okay. Yeah. Then a determinant is equal to product of all eigenvalues of the matrix. So it is kind of product of all the eigenvalues. So it will represent the change in volume and all, like, because generally we are dealing with orthogonal matrices where every eigenvalue is denoting a particular direction, a different direction, and scaling in different directions will change the volumes accordingly. So determinant will give us an intuition of how much volume is changing. If the determinant is 0, space is contracted completely along at least one dimension. Just said it here. Causing it to lose all volume. Yeah, because if determinant is 0, then one of the eigenvalues is 0. That means in one direction there is 0 scaling. 0 scaling means it's contracting to nothing, kind of. It's like contracting to a point. Okay. Principal component analysis. So if we have m points, a collection of m points, and you want to reduce the amount of data that is stored so that we can consume less memory and somewhat less precision, but still it's good enough to represent whatever we want to, like, show. So our task is to reduce the dimension of these points. If they are in n dimension, we want to reduce it to l dimension. So if we have one vector, we are going to apply an encoding function f to get some value f of x, which is xc they have mentioned. Then we'll apply decoding function g of f of x, which is roughly equal to x. Now this is in n dimensions. This is in L. This is again in N. Okay.
Andrea asked if we should do PCA next time. And that's a question for everybody, I think.
Yeah, I mean we can do PCA next time. Like, what are others' opinions?
Yeah, that's fine. I think that is the last topic. Yeah.
So, do like anyone, if anyone has a great intuition in PCA, they can also take the session. And I still have to I'll read it once again. But I mean, like, why and how is the direction people have proceeded in earlier?
I have a
Any
very
idea?
layman's intuition, like not this deep mathematical thing. But basically, like you decompose it, and it kind of becomes like from a sparse space to a dense space, and then you chop out some of the so essentially the decomposition results in an exact decomposition, but then you knock out the diagonal elements which are lower, like non-principal components, and that results in a denser, fuzzier space. But that is more good for semantic kind of things, right? Rather than like a sparse lexical kind of thing. So I think of it in terms of NLP, and not. I don't have this deep mathematical intuition. It's basically just like a overall thing.
Okay. And like, why is it even required to reduce the memory?
I was actually, I think of it not in terms of reducing the memory, but in terms of fuzzifying the space.
Okay.
Right. So you no longer have ones and zeros. You have things like 0.78, 0.53. So it becomes like a floating point thing. In fact, it might actually end up taking more space because now it's a dense matrix compared to if I had some sparse representation. But I think of it in terms of having more. It compresses the space and makes it semantically more suitable for lookup.
Okay.
I think it's, I don't know, the way I've seen it used is you have a lot of dimensions and people want to see what are the more meaningful, the dimension where there are more variants, and so you can look at, basically you look at less variables. Instead of having 1,000 dimension, you can plot your data in let's say 2D or 3D, and you can look at it this way. That's what I've seen people doing.
Yeah. So yeah, I mean, it is known as a dimension reductionality algorithm. Yeah, I think we can talk about it in the next session. So I just wanted a feedback about even today's session. Was it a bit slow, and how did you feel? Uh,
From
No,
my side, it worked well. Sorry.
sorry, go ahead.
Yeah. No, I'm done. Yeah. Sorry.
I felt it
okay.
good pace, and then it was good to see that we were able to go through each of those and develop an intuition about it. So that's what we would need with basics, right? We need to understand why we are doing something. So I think this space is good, and we can continue this way.
Yeah. Even my intuition was just to because we won't be looking back to these things again, I guess. So this will be used frequently. For example, positive definite matrices, and we'll always get that intuition ahead. But there are like 20 chapters in this book, and if we even, I mean, complete one chapter per week, it will take 20 weeks, which is roughly 5 months. So do you, do you guys have any timeline that you want to complete this book? I mean, is there any target deadline?
I have none.
Yeah, I too have nothing. Even if I complete in my lifetime, I will be blessed.
Great, great.
Yeah, more than completing it sooner, I would rather prefer completing it in a way I'm not left with any questions further. So if we finish a chapter, okay, all my doubts are solved and I understood it well before I proceed to the next one, because most of the later chapters will be dependent on some understanding of this, right? Like you're building on top of these things.
Yeah, absolutely.
Yes, yes. Great. Yeah, even I'm looking for a deeper mathematical insight, and with discussions, I think I'm getting newer insights which I never thought of earlier. So yeah, I think it's going good. So anything else anyone wants to say? Otherwise, we can conclude.
What do we want to do for next session, apart from the PCA?
Probability.
So we want
Yeah,
to
we
start
can.
reading. Yeah, sorry, go.
Yeah, we can do PCA and the third chapter, I guess, if everyone are comfortable with.
Yeah.
Yeah.
Yep.
Great. Okay then. Bye everyone.
Right.
Enjoy the weekend.
All right. Thank you for running this session again. Yeah. Thank you.
Thanks everyone. Yeah.
Yeah.
Bye.
Bye.
Bye.